You ever stop and think about what it would take to make everything around us, well, truly smart? And I'm not just talking about your phone or your smartwatch. I mean, think about your coffee maker, your thermostat, or even the tiny sensors that keep a bridge from collapsing. The big dream here is to cram some serious artificial intelligence onto the smallest, most common computer chips that honestly run our world. So, let's get into it.
I mean, it's a good question, right? We've got AI that can whip up poetry or paint a masterpiece, so why is your so-called smart toaster still just a toaster? Well, the answer really boils down to this fundamental clash between the world of giant AI and the world of teeny-tiny electronics.
And the potential here is just massive. Just imagine, for a second, sensors in a field that can spot crop diseases right there on the spot. Or maybe wearable health gadgets that can detect a problem locally without ever having to beam your private health data up to the cloud. That's the whole promise of what we call on-device AI, a field known as TinyML.
Okay, but here's the rub. The AI models that do all this incredible accurate stuff, they are absolute computational monsters. They're built to live in data centers with basically unlimited power and memory, not on a little chip the size of your fingernail. To really put this into perspective, just look at this number, 100 megabytes. You know what that is? That's how much memory you need just to process a single layer of a powerful AI vision model like VGG16. And these things have dozens of layers.
Now compare that to the hardware we're trying to jam it onto. A standard microcontroller, the little brain inside your coffee machine. It might have just a few hundred kilobytes of usable memory. We're not even in the same ballpark here. And this chart, wow, it just lays it all out, doesn't it? The scale of the problem is just staggering. We are talking about a memory gap of 2 orders of magnitude. 100,000 kilobytes needed for the AI versus maybe 340 available on the chip. So the million-dollar question is, how on earth do you bridge that gap?
It just seems totally impossible. It really is like trying to stuff an elephant into a shoebox. I mean, you can't just shrink the elephant down and expect it to still be an elephant, right? And as we're about to see, you can't just shrink an AI model and not expect some pretty serious consequences.
So, okay, how do we solve this whole elephant in a shoebox problem? Well, the answer lies in this really exciting field called TinyML. And trust me, it's one of the coolest frontiers in tech right now, where AI meets the world of tiny embedded systems. So what is TinyML really? At its heart, it's all about making our devices smarter, more independent, and way more responsive, all without them needing to constantly phone home to some server in the cloud. And the perks? Oh, they are huge. For starters, you get way better privacy because your personal data never leaves the device. It also means you get faster, real-time decisions because you're not waiting on a network connection. And it's incredibly efficient. We're talking devices that can run for years on a single tiny battery.
You might be thinking, well, why not just build smaller AI models? And yeah, researchers have tried that. There are all these tricks like model compression and pruning, but they almost always come with a price tag. You lose accuracy. And let's be honest, an AI that's not accurate isn't really all that smart, is it?
Okay, so this brings us to a seriously clever workaround. If you can't actually fit the whole elephant in the shoebox, what if you could process it just one little piece at a time? The technique is called swapping, and it's actually an old-school idea from computer science. The basic idea is, instead of trying to load the entire AI model into the microcontroller's tiny little memory, you keep the big, bulky parts of it on cheaper external storage, like a simple SD card. So here's the play-by-play. The system takes that massive AI layer and chops it up into these small, bite-sized pieces called tiles. Then it loads just one tile from the SD card into memory, runs the numbers, writes the answer back to the card, and then just grabs the next tile. It just rinses and repeats this over and over until a whole job is done.
Now, I know what you're thinking, because it's exactly what the researchers thought. Hold on a minute. This sounds incredibly inefficient. All that back and forth reading and writing to an SD card, that's got to be super slow, it's got to destroy the card, and it must use a ton of battery power, right?
Well, this is where it gets interesting, because the results were pretty surprising. First off, it turns out the microcontroller can do its math while it's swapping in the next piece of data, so a lot of that delay is basically hidden. Second, most of the work is just reading data, which doesn't wear out an SD card nearly as much as writing to it. In fact, research showed a card could last for over 7 years. And finally, the extra energy cost? Pretty modest, less than a 42% increase in the absolute worst-case scenario. The elephant fits.
But you know how it goes in tech. You solve one huge problem, and sometimes you create a completely new one. By making these tiny devices smart enough to run this sophisticated AI, we've also, unintentionally, painted a giant target on their backs.
And here it is, the heart of the new problem. Those same tight constraints, not enough memory, not enough processing power, that make it hard to run the AI in the first place, well, they also make it nearly impossible to run any kind of traditional security software. There's just no room.
I mean, think about it for a second. These devices aren't locked away safely in some secure data center. No, they're out there, in the real world. They're in our homes, on our city streets, inside our factories. They are physically accessible to anyone, and now they're holding incredibly valuable intellectual property, the AI model itself.
This just blows the doors wide open for new kinds of attacks. Attackers can go after the physical hardware itself, they can mess with the software, or they can even attack the AI model directly, trying to either fool it or just plain steal its secrets.
Let me give you two really powerful examples. With physical access, an attacker could pull off what's called a side channel attack. They can literally listen to the chip's power usage as it works and use that to reverse engineer and steal the AI's secret recipe. Or they could try an adversarial attack, where they create a sneaky input, like a carefully designed sticker they put on a stop sign that's invisible to you and me, but it tricks a self-driving car's AI into thinking it's a speed limit sign. The consequences could be catastrophic. So at the end of the day, we're left with this really delicate balancing act. TinyML gives us this incredible, world-changing power, but it comes bundled with some pretty significant peril.
This table really sums up the constant trade-offs. On the one hand, we get the ability to run these huge, super accurate AI models, but we risk slowing things down. We get to use cheap, everyday hardware, but now we need to add external storage. And while we get amazing data privacy by keeping things off the cloud, we expose these devices to a whole new world of physical attacks.
And that really is the fundamental question that's going to define the future of this technology. The ability to put intelligence absolutely everywhere is here, it's now. The challenge going forward is figuring out how to do it safely, how to do it securely, and how to make sure these trillions of tiny new brains are working for us and not against us.
Okay, let's unpack this. Imagine a future where your smart devices don't just see and hear, but truly feel. We're talking about mimicking the incredible complexity of human touch, but building that intelligence into the tiniest, most power-constrained devices imaginable.
Right.
Today, we're taking a deep dive into some truly fascinating research from Hamoud Wayouns and his team at the University of Genoa.
Yeah, it's really compelling work.
This deep dive is our shortcut to understanding how we can bring advanced machine learning, the kind you usually need supercomputers for, right to the very edge of computation.
Directly where the data is sent.
Exactly, and what surprising design principles make it possible.
What's compelling here is how this research confronts a fundamental paradox. How do you put powerful, data-hungry machine learning algorithms onto hardware with incredibly limited resources?
Yeah.
Their core mission is to enable real-time tactile data processing using embedded machine learning, and they're doing it through innovative hardware accelerators and something called approximate computing techniques. We're talking about monumental reductions in hardware size and power consumption, all without sacrificing significant accuracy.
Wow.
The big question this work implicitly asks is, how much can we push efficiency without breaking performance or, even the user's perception of performance?
So if we're trying to build electronic skin that can really feel and put that capability onto tiny battery-powered devices, what's the biggest wall they hit? My initial thought is that processing all that rich, tactile data with complex AI sounds like a fundamental contradiction in terms.
You're absolutely right. That's the core challenge.
Okay.
Our own skin is, well, it's a marvel, converting chemical, thermal, or mechanical stimuli into electrical signals that our brain interprets with incredible speed and nuance.
Right.
To mimic that with electronic skin means handling a massive amount of tactile data in real time. Traditional machine learning algorithms, especially the deep neural networks we hear so much about, are notorious power hogs and memory monsters. Sending all that data to the cloud for processing introduces delays that are unacceptable for something like a robotic arm that needs to react instantly.
Okay, so latency is a big killer too.
Exactly. So the constraint isn't just power, it's also latency. The source material highlights this, emphasizing how computational complexity and the choice of hardware platform are truly critical factors.
So we're essentially talking about giving devices a sense of touch that's not just basic, but sophisticated enough to, say, tell the difference between brushing a paintbrush and rolling a washer.
Precisely. Common tactile applications include things like precise grasp control in robotics, manipulating delicate objects, identifying surface textures,
Mm.
and that specific example you gave, touch modality classification, distinguishing those nuanced actions like brushing a paintbrush, rolling a washer, or sliding a finger.
Yeah.
To even get to that point, you often need to clean up and simplify the raw sensor data. Think of pre-processing steps like principal component analysis, or PCA,
Right, PCA.
which can take complex, multidimensional data, maybe like a 3D scan of a touch, and boil it down to its most essential 2D features.
Kind of simplifies it.
Yeah. Or independent component analysis, ICA, which helps untangle multiple overlapping contact areas on a sensor surface, like separating individual voices from a crowd, allowing us to identify each unique touch interaction.
Ah,
These steps simplify the problem before the heavy-duty machine learning even begins.
here's where it gets really interesting, and I admit it sounds almost counterintuitive. The team's approach centers on something called approximate computing techniques, or ACTs.
Mm.
It sounds like we're intentionally making things less perfect to gain huge efficiencies. Are we just saying good enough is, well, good enough?
It's a bit more sophisticated than just good enough, though that captures some of it. The underlying principle behind ACTs is that many applications, especially in machine learning, have an inherent tolerance for some level of inaccuracy. Not every calculation needs to be perfectly precise, and not every bit of memory needs maximum reliability. By strategically relaxing some accuracy constraints, we can achieve substantial reductions in computational and memory requirements.
So you trade a little bit of perfection for a lot of efficiency.
Exactly. The dissertation outlines several algorithmic-level ACTs. For example, quantization means reducing the bit width of data. Think of it like simplifying a high-definition image to a lower resolution to save space, but still keeping it recognizable.
Gotcha.
Loop perforation involves skipping certain iterations of a computational loop, and data sampling reduces the input size, perhaps by downscaling or downsampling the sensor readings.
Interesting.
The real insight here is that for many tasks, this good enough approach, if intelligently applied, delivers massive gains without a noticeable hit to performance from a user's perspective. There's always a quality configurable knob to finally balance the trade-off between accuracy and performance.
That makes perfect sense. It's like you don't need a super precise calculation for every single detail if the overall outcome remains accurate enough for the task at hand.
Precisely.
But where's the line? Are there any applications where this good enough approach simply wouldn't be acceptable, where even a tiny bit of inaccuracy could be catastrophic?
That's a crucial question, and it really speaks to the art of applying ACTs.
Yeah.
You wouldn't use it for, say, medical diagnostics where precision is absolutely paramount,
Right, makes sense.
or in financial transactions where a single bit error could be disastrous. But for many perception tasks like touch recognition, object detection, or voice commands where our own biological systems are inherently approximate and robust to minor errors, ACTs shine.
So it's about matching the technique to the application's tolerance.
Exactly. It's about understanding the application's true tolerance for error and exploiting it.
To really see these approximate computing techniques in action, let's dive into how they revolutionized a classic, often computationally heavy algorithm. K-nearest neighbor, or KNN.
Ah, KNN.
Yeah. It's a fundamental classification algorithm. But how did they make KNN, which can be quite demanding, work efficiently for tactile data on these tiny devices?
Well, the KNN algorithm is pretty elegant. It classifies a new input based on the majority class of its nearest neighbors in a training data set. The biggest challenge, especially with a large number of stored data points, isn't just calculating all those distances, but then sorting them to find the K closest ones. Traditional sorting algorithms are very memory and computation intensive.
Right. Sorting takes time and power.
A lot. So this research introduces a novel, selection-based sorter. Instead of sorting the entire list of distances, which is like trying to rank every runner in a marathon just to find the top 3.
Yeah, inefficient.
Very. This selector directly identifies just the K minimum distances. It's far more efficient.
That's a clever way to bypass a massive bottleneck. What kind of impact did this have? Did it, speed things up a lot?
Oh, definitely. This innovation alone significantly reduces hardware area by up to 48% and provides a speed up of up to 4.5x compared to conventional sorting algorithms.
4.5 times faster.
Yeah. For example, in hardware synthesis, their custom selector took only 15 quad cycles compared to 96 for a traditional botonic sorter.
Wow, 15 versus 96, that's dramatic.
It's a dramatic reduction in processing cycles for a similar hardware footprint.
Those are impressive gains. And I'm curious about the practical side of this research, specifically how they actually implemented this KNN on real hardware. Did they put everything on one tiny chip?
What's compelling here is their intelligent hybrid approach for hardware implementation. They recognize that some parts of the algorithm are more computationally demanding than others.
Okay.
So they designed the system so that the heavy lifting, the distance calculation, happens on a specialized, high-performance part of the chip, specifically an FPGA.
The field programmable gate array, right. Good for parallel stuff.
Exactly. Meanwhile, the less demanding tasks, like the sorting of those k-minimum distances and the final majority voting to determine the class, are offloaded to a more general-purpose CPU. This intelligent division of labor optimizes for both speed and energy.
Smart. So how did it perform in real life?
When implemented on a specialized edge device platform, their exact KNN classifier could perform real-time touch modality classification in just 25.7 microseconds.
Microseconds. That's incredibly fast.
Incredibly, consuming only 6 microjoules of energy, that's really efficient.
Tiny energy costs.
Right. And then, when they applied ACTs, specifically downscaling, which means reducing the number of sensor readings and data format modification by using fixed-point arithmetic instead of floating point.
Ah, fixed point. Less precise, but way faster on simple chips.
Exactly. Think of fixed-point arithmetic as using integers with an applied decimal point, much more efficient for constrained chips. This approximate KNN delivered a 2.3x speedup over the already fast exact version, a 69% energy reduction compared to the exact one, and a 56.4% average hardware area reduction, all with an accuracy degradation of, at most, 2.6%.
Wow. So huge gains in efficiency, barely noticeable drop in accuracy.
Pretty much. A fantastic trade-off for this kind of application.
That's a truly remarkable balance of performance and efficiency. What does that kind of speed and low power mean for someone using, say, a prosthetic hand?
Well, it's transformative. It means near instantaneous touch recognition, allowing a prosthetic hand to react immediately to the environment. Like you touch something hot, it reacts now.
Right, no lag.
Exactly. Minimal power draw means longer battery life, making the device practical and comfortable for everyday use. This isn't just an incremental step, it's a leap forward in how intelligent devices will interact with our world.
Making them truly responsive.
And seamlessly integrated into our lives.
That's incredible for a foundational algorithm like KNN. But tactile data isn't always simple, flat points. Sometimes it has rich spatial and temporal dimensions, like a video of a touch. How do we tackle that complexity, especially with something like tensorial support vector machines or TSVMs? The tensorial part alone sounds complex.
You've hit on a crucial point. If we connect this to the bigger picture, tactile data often comes in multidimensional formats. Imagine a 4x4 sensor array providing readings over time.
Like a little movie of the touch.
Exactly. Representing this as a tensor is vital because it preserves its inherent structure and relationships, much like a video captures both space and time, which is incredibly valuable for accurate classification.
Okay.
TSVMs build on the idea of support vector machines, which are known for finding optimal boundaries to classify data, now extended to handle this rich, multidimensional tensor data.
Got it. But I'm guessing there's a catch, computationally.
There is. A key mathematical step in TSVMs is singular value decomposition, or SVD.
SVD, right. Powerful but heavy.
Very heavy. SVD is a powerful mathematical tool that helps break down complex data into its fundamental components, much like analyzing the key ways the surface interacts with the sensor. But traditionally, it's a computational monster, incredibly intensive.
A massive bottleneck.
Exactly. A massive bottleneck for embedded systems demanding large hardware areas and high power consumption.
So if SVD is such a computational bottleneck, how did they manage to make TSVMs practical for edge devices without compromising on the benefits of tensor data? Did they find a clever approximation for SVD2?
They did, and it's really groundbreaking. This research proposes replacing that traditional brute force SVD computation with a shallow neural network.
Using a neural network to approximate SVD.
Yeah. Instead of complex matrix decomposition, a specialized small neural network is trained to predict the singular vectors.
Wow. How much faster is that?
It's staggering. This isn't just a minor improvement. It leads to a 324x speedup for SVD computation.
324 times.
Yes. with 58% less hardware and 67% less power compared to traditional SVD algorithms like the Jacobi method, which are far too heavy for edge applications.
That's incredible.
And when this NN-based SVD is integrated into the full TSVM architecture, they achieve a 131x classification speedup and a 50% power reduction, classifying tactile data in just 36 milliseconds.
So fast enough for real-time interaction again.
Definitely. And here's another critical point that speaks to the future: scalability.
Ah, right. How well does it handle more data?
When the number of training tensors doubles, the traditional Jacobi-based TSVM saw a significant 29% increase in hardware resources needed.
Okay, that's not great if data grows.
No. Their NN-based TSVM, however, required less than a 1% increase in hardware.
Less than 1%. That's amazing scalability.
It makes it incredibly robust for handling larger and larger data sets in the future without constantly needing new, bigger chips. Truly makes you wonder, how many other complex mathematical operations we've been over-engineering, assuming absolute precision was always necessary, when a specialized neural network could approximate them so much more efficiently.
That's a really good point. Okay, from reinventing classic algorithms like KNN to approximating complex math for TSVMs, this deep dive is truly showing how specialized AI for touch is becoming a reality. Now, let's talk about the big guns of machine learning. Convolutional neural networks, or CNNs. They're powerful, yes, but notoriously resource-hungry.
Heavy hitters, yeah.
How did they get CNNs, which usually need powerful GPUs, to work on these tiny, often the most constrained devices?
This part is all about striking a very clever balance. Full precision CNNs, which use many bits to represent their weights and activations, are indeed very accurate but far too complex for edge devices.
Way too big, way too power-hungry.
Exactly. At the other end of the spectrum are binary convolutional neural networks, or BCNNs. These drastically reduce complexity by using just one bit for weights and activations.
Super efficient.
Incredibly efficient, but often comes with a significant accuracy drop. You lose a lot of nuance.
Right, the performance suffers.
Often quite badly. So the solution proposed here is a hybrid precision binary weight network, or HBWN.
Okay, hybrid. Mixing things up.
Exactly. It's a brilliant compromise. The first and last layers of the network, which are crucial for initial feature extraction and final classification, use a slightly higher precision, specifically 16-bit fixed-point activations with binary weights.
So keeping some precision at the start and end.
Right where it matters most. But the hidden layers in between, where most of the computation happens, are fully binarized. One bit.
So they're essentially giving precision where it truly matters in those critical input and output stages, but going for maximum efficiency in the middle, that's a very smart way to get the best of both worlds.
It is. The efficiency of binarization where it makes the biggest difference, and higher precision where it's absolutely critical for retaining accuracy.
And did it work? How was the accuracy?
What's compelling here is the dramatic accuracy boost this hybrid approach achieved. Traditional BCNNs only managed around 30–40% accuracy for touch modality classification. Pretty poor.
Yeah, not very useful.
But the HBWN, using this intelligent hybrid strategy, jumped to over 71% average accuracy and even up to 77.88% in its best configuration.
Wow, that's a huge jump, getting close to full models.
It's comparable to the much larger full precision SVM and deep CNN models, but with a massive 99.99% reduction in operations and model size.
99.99% reduction.
Yeah. It's so compact it fits within 5 KB of memory.
5 kilobytes, that's tiny.
Tiny, making it suitable for even the smallest microcontrollers you can imagine.
Incredible. And the performance on hardware, speed, power.
When implemented on that specialized edge device platform we mentioned, this HBWN accelerator achieved real-time classification in just 0.8 milliseconds.
Less than a millisecond.
Consuming a mere 53 milliwatts of power. That translates to an energy per classification of 42.4 microjoules.
Still super low energy.
Demonstrating up to a 99% energy reduction and a speed up of up to 16875XX compared to existing solutions running on, say, a CPU.
Almost 7,000 times faster.
It's a testament to how intelligent architectural design, combined with thoughtful approximation, can unlock the power of deep learning for even the most constrained environments, proving that uniform precision isn't always optimal.
So what does this all mean for you, the learner, and for the future of intelligent devices? This deep dive into Hamoud Wayun's dissertation shows us a clear, actionable path to building incredibly responsive, energy-efficient electronic skin systems.
It really lays out a roadmap.
From optimizing classic algorithms like KNN with clever sorters, to transforming sophisticated ones like TSVMs by approximating their most intensive steps with compact neural networks.
Right.
To re-architecting deep learning giants like CNNs into hybrid precision networks, the overarching message is clear. By intelligently and strategically trading off a little precision, we can unlock immense performance gains
Huge gains.
and embed advanced AI directly into the fabric of our world, right at the point of interaction.
Indeed. The implications are profound. This isn't just about faster or cheaper computation, it's about enabling entirely new capabilities for robotics, prosthetics, and countless IoT applications that demand real-time, nuanced tactile intelligence.
Things that just weren't possible before on small devices.
Exactly. The ability to perform complex machine learning on minimal hardware with orders of magnitude less power and faster response times moves us closer to truly ubiquitous intelligent edge AI.
Yeah.
A key takeaway from this research is that innovation often lies not just in new algorithms, but in rethinking the fundamental assumptions of how we compute.
Challenging the need for perfect precision everywhere.
Precisely. It leads us to consider, as approximate computing becomes more sophisticated, where else can we apply this good enough principle to transform seemingly impossible computational challenges into practical everyday solutions?